Today we will discuss the fundamental theorem of calculus, but before we do that, we are going to examine a property of definite integrals involving what are called dummy variables. On the left-hand side here, you can see the definite integral from a to b of f of x dx, which is this blue area. If we change the variable name from x to t, what we see is that it's exactly the same blue area. In other words, the integral from a to b of f of x dx is exactly equal to the integral from a to b of f of t dt. It does not matter what we call a variable. When we're done, we get the same area. So the variable name makes no difference. It's what's called a dummy variable. And we will make use of this property when we define the area function. Here we have the curve y equals f of t, and this time instead of going from a to b, we want to go from a to x, where we will allow x to vary. So the area function will be under the curve between a and x is allowed to vary. A is a fixed point here, and the reason that we picked the variable t is x is the upper limit. It cannot also be the variable that describes the curve between there. So this is the notation that we use for this area function. Notice, however, it's a function of x depending upon where the right-hand endpoint is, not the name of the variable that we use for the function. Now, as an example, let's take a look at the following function and define the area function a of x to be from 1 to x integral f of t dt. So a of 1 is 0 because it is the integral from 1 to 1. There's no area. We get 0. A of 2 is the integral from 1 to 2. That's an area with the base being 1 and the height 2, rectangle 2. So a of 2 is 2. A of 0 is minus 2, and the reason is we are going from 1 to 0, going backwards. Delta x is negative, height is positive. That's going to count as negative area. And finally, a of 5, which is the integral from 1 to 5 of f of t dt, is minus 1 because there's positive area of 2 plus 1 on the top and negative area of 4 on the bottom. Now we ask the question, what is the derivative of this area function? So a of x is this integral from a to x of f of t dt. Again, a is some number we picked and x varies. The derivative is going to be the limit as h goes to 0 of a of x plus h minus a of x over h. And we want to see what that is. So the integral from a to x is represented by this area, which is a of x. The integral from a to x plus h is represented by the somewhat larger area. And the difference between this and this is this little area, the area between x and x plus h, and that's the area function of x plus h minus the area function of x. Now, what we're going to do is expand this little section and observe that someplace in here is the smallest height that you're going to see, and that's going to be at u. And somewhere in here is the largest height you're going to see, and that's going to be at v. If we look at the area of this region, it is bigger than or equal to the rectangle we get when we use the smallest height as the height of the rectangle. And it's going to be less than or equal to the area of the rectangle we get when we use the biggest height. So minimum value of f on the interval times h, maximum value of the function times h, and the actual area is in between. So f of u times h, which is the min value, less than or equal to a of x plus h minus a of x, less than or equal to f of v times h. And when we divide through by h, we get f of u less than or equal to this expression that we're looking for, less than or equal to f of v. And now that information is recorded up here. And now what we want to do is look and see what happens when h goes to 0. And you can see as this interval compresses, u is going to be forced towards x, v is going to be forced towards x. So this is almost a pinching theorem. And as a result, as h goes to 0, f of u, since f is continuous, goes to f of x, and as h goes to 0, f of v goes to f of x. And we discover that this thing, which is trapped in between, must go there as well. So by the pinching theorem, a prime of x is f of x. And that is the fundamental theorem of calculus. Suppose that f is continuous. Then the area function, which is the area under the curve between a and x of f of t dt, exists, and the derivative is f of x. Now, we have bypassed the part of this where we show that the area exists. That's a more sophisticated issue, but be assured that if f of x is continuous, that area does exist, and the fundamental theorem tells us what that derivative is. So here's the fundamental theorem again. Let's see what it says. It says the derivative of the area function is f of x, where f is the function that gives you the curve. So in this case, sine t cubed is the function that gives you the curve in t, so the derivative is sine x cubed, because this is a function of x. Another example, let's take the derivative from x to 1 of sine t over t squared plus 1. Now the problem here is our theorem says the integral from a to x, and this is the integral from x to 1, which is playing the role of a. So the theorem doesn't quite apply as written, but we know something about flipping limits. So if we do flip the limits, we do get an integral that looks exactly like this, and there's a minus which just factors out, and the answer ends up being minus sine x over x squared plus 1, which is just what you get when the integrand variable t is replaced by the variable x. Last, let's look at the derivative of a more complicated expression. Integral from 2 to x squared of the square root of t to the 4th plus 1 dt. Now the difficulty here is there isn't an x here, there's an x squared. So let's look at what we would get if we had an x there. And this would be a standard area function that we know about, and we would know its derivative was the square root of x to the 4th plus 1. Now if we look at this, what we can see is a of x squared is the integral in question. So what we're going to do to find this derivative is we're going to differentiate a of x squared. And that's just a chain rule. And we're going to get a prime of x squared times 2x. And now we know a prime is the square root of x to the 4th plus 1. So when we substitute in x squared every place we see an x, we get an x to the 8th, which is x squared to the 4th plus 1, times the derivative of x squared, which is 2x. Now what we're going to do is look at a slightly different form of the fundamental theorem. We know at this particular point that the derivative of the area function is the curve. And we're going to use that to find a slightly more useful form to evaluate definite integrals. So let's imagine that capital F of x is an antiderivative of f of x. And that means the derivative of cap f is little f, which you'll notice is also the derivative of the area function. So based on what we know about antiderivatives, the area function is f of x plus some constant. And the question is, what's the constant? Well, if you put x equals a into here, the area is 0. So a of a is 0. Plugging that into here, we get 0 equals f of a plus c, and c is minus f of a. So the area function is cap f of x minus cap f of a. And if we look at the definite integral from a to b of f of x dx in terms of the area function, that's just a when x equals b, so that's a of b. Plug in here, f of b minus f of a. And what that says is the definite integral from a to b of f of x dx is cap f of b minus cap f of a, and that is part 2 of the fundamental theorem. So if we have a continuous function, we have an antiderivative, then the definite integral from a to b of little f of x dx is capital F of b minus capital F of a. Let's do a quick example illustrating the use of this second form of the fundamental theorem. Okay, we'll start with the definite integral between 1 and 3 of x squared dx. And the fundamental theorem says find yourself an antiderivative and then calculate f of b minus f of a. So x squared is known to have the antiderivative x cubed over 3. So using our formula here, we get f of 3 minus f of 1, which is 3 cubed over 3 minus 1 cubed over 3, which is 26/3. Suppose we had chosen a different antiderivative. So f of x equals x cubed over 3 plus 4 is an antiderivative for x squared. And according to the fundamental theorem, we ought to be able to use it. We use the fundamental theorem, we get f of 3 minus f of 1, which is 3 cubed over 3 plus 4, minus 1 cubed over 3 plus 4, which is again 26/3. And as you can see, what's happened is the 4's have canceled. So it doesn't matter what antiderivative you choose to use this fundamental theorem. So you should choose an antiderivative that makes your calculation relatively easy.